Hello, it's Christian, the CTF noob again, and today we're going to have a look at a third behemoth challenge from OverTheWire. This time we don't have to overflow a buffer, but still need to find a way to get a shell. So let's get started with behemoth2. As always, we start by connecting to the challenge server via SSH. Then we have a look at what files we have to work with. Again, we only have the executable and nothing else, so let's run it. We get the message that touch can't create a file because the program doesn't have the required permissions. Maybe we create a temporary directory and try to run the program again. We still get a permission denied message, but I guess that's only due to missing permissions on the directory, so I'll just give everybody all the rights there are on that directory and we should be fine. Now, when I run behemoth2 again, I don't see the permission denied message anymore. But the program seems to wait for something and doesn't react to my input. So let's stop the process and see if any files were created. Running ls, I can see that a file was created and its name looks like a process ID. If I inspect the contents of the file, I can see that it's empty. Okay, so behemoth2 created a file, but what else does it do? Maybe running the program again with ltrace gives us something to work with. So the program starts with libc start main and then gets the process ID. Afterwards, it uses sprintf to create a touch command with the process ID. Then it runs lxstat. The Linux standard base specification states that lxstat has the same behavior as lstat as specified by POSIX. And the man page for lstat states that these functions return information about a file. No permissions are required on the file itself, but in the case of stat and lstat, execute search permission is required on all the directories in path that leads to the file. I guess that's used to test if the file already exists or not, but for now that's not important. After that, get effective user ID is called twice, and set real user ID is called afterwards. The system is used to execute the touch command. Finally, the program sleeps for 2000 seconds, which is more than half an hour. Okay, so what do we know about behemoth2? It executes a touch command, which doesn't seem too bad. But it uses the touch command as defined in the path variable and does not use an absolute defined path. So we should be able to try behemoth2 into using a touch command that we provide. For that, I create a file that I call touch and simply add the string /bin/sh. This now is a valid bash script that I can make executable. If I run the script, I get a shell, but of course I'm still behemoth2. Now I'll prepend the temp directory to the path variable. When looking for an executable, the path variable is scanned from front to back. So if our touch shell script comes before the real touch command, behemoth2 should execute our shell script. Let's try it out. For testing purposes, I simply echo out the results of prepending the temp directory to the path variable. That all looks okay, so let's try to call behemoth2 with a tempered path variable. Nice, we have a shell, and since behemoth2 called our script, the user should be behemoth3. Let's test this with whoami. Yep, we are behemoth3. So let's get a password for the next stage and we're done. As last time with behemoth1, I also want to have a quick look at the disassembly this time. For this, I open behemoth2 with GDB, and then set a disassembly flavor to Intel. Finally, I disassemble the main function. The interesting part starts at the compare at main plus 84. Right after that comes a jump, so we'll set a breakpoint here. At main plus 137, we can see a call to system, so it makes sense to also set a breakpoint there and see what command gets executed. Then at main plus 210, we can find a second call to system. This is also worth a breakpoint. So let's run the program. We stop at the first breakpoint right before the jump. Let's have a look at the registers. The value in EAX is OXF000 and not OX8000. This means that the execution will not jump. Let's continue. We break at the first call to system, and EAX should contain the string that will be executed. So let's inspect EAX. It contains the touch command that will create the file. This is what we already saw when running the program outside of GDB. Okay, so we continue. And end in the long sleep, which we already know. Let's run the program again and this time trigger a jump. For this, I set the EAX register to the expected value 0x8000. Okay, EAX contains the correct value, so let's continue. We land directly at sleep. So I stop the execution and run the program again. Then I continue after the first breakpoint, and at breakpoint 2 I set EIP to 0x08048609, which is the instruction after the call to sleep. If I now continue, GDB stops at the third breakpoint, which is the second system call. So let's have a look at EAX to see what this system would have executed. Well, it's just running the cat command on the existing file. Maybe we didn't find much valuable information in analyzing the executable, but at least we exercised reading disassembly. Okay, so that was a quick one, and as last time, we didn't even have to look at the disassembly. Still, I hope you found this video interesting. If you liked the video, please give it a like, and if you want to see me solving more CTF and wargame related challenges, please subscribe to my channel. If you have any feedback or other challenges I should have a look at to learn more on the whole security topic, feel free to leave a comment under the video. Thank you and until next time.